Our project is assessing the viability of Allegheny Minerals' entrance into the thermoplastic filler market. My name is Greg Simon, and my partners are Laekynn, Proctor, and Zachary Potter. Our advisor is Mr. Jason Williams, and our sponsor is Allegheny Mineral. Background on calcium carbonate is an inorganic filler and is typically used as an extensional filler, meaning it takes up space in the polymer matrix of your material and just adds a density to it. Typical particle sizes range from about 1 to 50 microns, and loading levels are around 5 to 50%. And it's typically compounded with polyethylene and polypropylene because they're both inexpensive materials. But these two materials aren't compatible for processing, but I will explain that in a later slide. The goal of this project is to determine whether it is feasible to use Allegheny Minerals calcium carbonate as a thermoplastic filler by evaluating the mechanical and thermal properties in comparison to market standard compounds within the thermoplastic market and offering recommendations to Allegheny Mineral for widening their market opportunities. So an overview of Allegheny Mineral is a limestone mining company located in Slippery Rock, Pennsylvania. They have a total of about 6 quarries, and it produces about 3,000 tons of calcium carbonate annually. It was specified that the particle size is on average of 71 microns, and it's achieved using a number 200 mesh, which is about 75 microns. The average purity of the product was about 91.9% calcium carbonate. So the current applications for the product is for mineral filler, for roofing and flooring, asphalt filler, concrete filler, coal mine rock dust, agricultural lime, which is also called ag lime, and livestock and poultry feed supplement as well. So the market standard compound we'll be using to compare Allegheny Minerals material to is called Vicron 4018. It has a particle size of about 8 microns with a purity of about 97% calcium carbonate. This material is specifically designed for thermoplastic fillers and is characterized as a high brightness material, so it is an all-white material shown in the top right. And it is also a ground material, meaning that this is also mined out of the ground and refined as well, and that's exactly what we're doing with Allegheny Minerals product, so that's why we chose to compare these. So areas of concern for this project, first is dispersion of the calcium carbonate, dispersion being defined as the even distribution of the filler throughout the polymer. This is important for this project because we need to have even distribution of the fillers so we get accurate and consistent testing results. If we don't get good dispersion in our materials, we'll get agglomerates, and agglomerates in the material can cause premature failure during the testing and throw our testing results off. This is because agglomerates form stress concentrations in your material and can cause premature failure. We're also concerned about the particle size. We need to make sure the Vicron and the Allegheny Minerals material are within a similar particle size so they're comparable, and it's also important to look at the aspect ratio of our materials, which is the length and diameter of our particles. We do not know this for this project, but it's essential in knowing finding any differences in our mechanical testing data, especially working with larger and smaller particles. Calcium carbonate is a polar molecule, means it's hygroscopic, which means it absorbs material and it absorbs moisture on the surface of the material, and it will stick to wet things. Polyethylene is a non-polar molecule and it's non-hygroscopic, so it will not absorb moisture on the surface. So this makes these two materials not compatible for processing, meaning if we were to take polyethylene and calcium carbonate, mix them together and process it, we'd get a lot of pellets with some calcium carbonate and some with none. So to compatibilize these materials, we coated the polyethylene in mineral oil, and then we poured on the calcium carbonate and then mixed it and then processed it. And that's how we got a good dispersed testing materials for our project. So the theory behind this project, filler dispersion is affected by the formation of agglomerates. Smaller particles increase dispersion with processing parameters and sample preparation. Also from research, we found that particles that are 25 microns and larger can mechanically perform worse than smaller particles, and particles with higher aspect ratio can mechanically perform better than smaller particles because longer particles can transfer stress better. And from this slide is how we constructed our hypothesis for this project. So the hypothesis for this project is after sieving Allegheny Minerals calcium carbonate to a maximum particle size of 25 microns and compounding with polyethylene at loading levels of 5, 10, 15%, it will provide an overall mechanical performance, including tensile, impact, and flexural testing results within 12.5% of Vicron's 4018 calcium carbonate of 8 microns.
In order to assess and compare our material, we followed a very specific testing plan. Within this testing plan, we prepared our material, and from there we compounded it. We ran thermogravimetric analysis and injection molded all of our parts. After running TGA, we sent our 3 types of calcium carbonate out to University Park for a particle size analysis to be completed. After injection molding, we completed tensile testing, flexural testing, impact testing, and ran differential scanning calorimetry, also known as DSC. It was important to make sure that we were getting similar loading levels in terms of our calcium carbonate and polyethylene compounds. For our 5% loading level, we had an average of 5.38 plus or minus 0.4 for that of the Vicron refined and unrefined material. Additionally, our 10%, we had an average loading level of 9.9 plus or minus 0.4. For our 15%, we had an average loading level of 12.86 plus or minus 0.2. We ran optical microscopy to ensure that our calcium carbonate was evenly dispersed throughout our polyethylene matrix. You can see in all 3 images below that we were able to achieve that.
This slide presents an average stress and strain data derived from the 50 mm per minute tensile testing at the 5% loading level, averaged from 5 samples. The refined material exhibits a distinctive behavior compared to the unrefined and Vicron materials. This showcases different mechanical resilience under low strain rate conditions. Here, we focus on the tensile modulus data derived at the 50 mm per minute strain rate at the 5% loading level. The graph compares the tensile modulus of the refined Allegheny mineral calcium carbonate against Vicron. The refined version shows a significant decline in tensile modulus, highlighting its reduced structural integrity at low loading levels. This slide displays the tensile modulus data at a higher strain rate of 500 mm per minute, specifically at the 5% loading level. All materials, including Vicron, refined, and unrefined Allegheny mineral calcium carbonate, demonstrate similar mechanical properties at this increased strain rate, suggesting comparable performance under rapid loading conditions. On this slide, we review the impact strength data captured by the Ray-Ran impact tester at the 5% loading level. The graph visualizes the robustness of each material type to sudden impacts, essential for applications where durability under shock is critical. Overall, our findings indicate that refined Allegheny mineral material underperforms mechanically compared to its unrefined counterpart, particularly at the 5 and 10% loading levels during the 50 mm per minute tensile testing. These results deviate significantly from Vicron and exceed the hypothesized 12.5% variance. The alterations in particle size and aspect ratio are likely due to the refining process and likely contributes to this discrepancy. In conclusion, our research leads us to challenge our initial assumptions. The data speaks clearly. The hypothesis that refining particle size would enhance tensile testing performance is not supported. In fact, our study suggests the opposite, that Allegheny Minerals' current unrefined product may already be optimally positioned for the market, without the further need for refinement. Therefore, we recommend that Allegheny Mineral capitalize on their existing market specifications to pursue market opportunities as they stand, leveraging the inherent qualities of their unrefined material.